Yeah. So I guess the outside has come into inside. There were, yeah, okay, it's still coming in. Uh, right, so this is the first time I'm coming to ICTS. I have heard a lot about it. And I am absolutely finding out that whatever I had heard was very true. That this is really like an island for scientists where scientists are like endangered species now, not only in India, in the whole world, I would say. But this is one place where people like us can congregate, talk to each other, make merry, and live the science that we do, which is absolutely fantastic. And I don't think such facilities exist. Too many of such facilities exist in India, which is a pity. But these buildings are also wonderful. I mean, because I get reminded of the time I spent in ISC. ISC, of course, has completely given up its character. It has these big, big buildings, which all of them look identical. Here you have those, stone is what Bangalore stands for. This entire region. If you ever went to Vijayanagar, that is Hampi, you would see fantastic structures of stone which have all collapsed now, but would still talk about what grandeur and what fantastic significance they had at one point of time. So this place still reminds me of places in IISc like the erstwhile JNC and NIAS, which was next to it. This is great. So and this meeting, we are a very small field here, and we are doing very much cutting edge research. And it is absolutely imperative that we talk to each other. And this kind of meeting is useful not only to know what we are doing, that of course that of course will happen, but to pass on the excitement to people who would hopefully follow us, put on our boots when we take them off. So what I'm talking to you, see, I am an experimentalist. I'm absolutely and completely an experimentalist. And I do things now which I have never in my life done before. I was trained as somebody who did atomic physics using light. And I developed techniques of measuring frequencies of lasers to part per billion accuracies and all that. I wanted to trap ions, which never happened. So from there, I moved on to some corporate making sensors using light, and then I thought corporate was completely stifling me, and I came back to academia, and I started working on stuff which I have never in my life worked on. This thing, optical tweezers. We had an optical tweezers. We were setting up an optical tweezers at IISc Bangalore, Vasant Rajan's lab, late Vasant Natarajan's lab. When I was leaving, there was this grand new microscope, sorry, and there was this project assistant who was not a student then, who needed my help in just turning on the laser and trying to couple it. But I had never ever trapped. Okay, atoms I had trapped, but particles, bigger particles using optical tweezers, I had never done in my life. The first time I did it was at IISER, and that also actually a couple of students did it, and three of us, IISER, that time we didn't have any PhD students, but we had these great MS students. Subhasish will know one of them at least, or Orijit Haldar, who is now a faculty at SN Bose. So he and another called Shombit, both of us, three of us, sort of set up this lab. And I remember we had this, I just got the microscope that my advisor had bought, Zeiss. And my throat was cut to pieces. Because then I realized that I had bought stuff which were completely unnecessary and whatever. So we had to reverse engineer the microscope because it was basically a fluorescence microscope. These Zeiss people had made merry out of my ignorance because I had never worked on a tweezers. And they had put in all kinds of filters and everywhere, which were happily blocking off the light that I wanted to put into the microscope to trap my particles. And we actually had to take off manually those filters. And there was one point of time when, thankfully, I was not in the lab, when Orijit actually took the microscope and reversed it. and put a vacuum cleaner and sucked out one optic. If I had seen it, I would have died on the spot, because you do not handle microscopes like that. Those were young people, and they also were unafraid. Thankfully, the microscopes, these are very, very robust beasts and all, right? So they didn't die. Thing is, when so anyway, I saw suddenly, I had gone to lunch, and I saw all of a sudden this beam was coming in. I said, what the hell? And then he told me what he had done, and I said, my goodness. Thankfully, I was not there. And then we aligned everything, and I had again gone for lunch, and the promise was that we'd all come back and start the experiment. And of course, as happened, they came back before me, and they were too much, the passion of youth, and they trapped before I had come. So I came in, and I saw that trapped particle, and I wanted to hit him, because I wanted to really press that thing, and wow, this is my trapped atom, and trapped polystyrene bead. And here it was sitting and laughing at me. Anyway, so I did not do that. But of course, after that, what we did here, this is a spinning thing. Here, of course, it has stuck. So if you see carefully, you would probably notice that there is a bit of, oh man, stopped again. Yeah. So this is spinning a little differently from that. I will be more clearer as I go on. But these are things this was done about 7 years back. 8 years back. This was done about 6 months back. Okay, so this story that I'm going to tell you is my evolution as in optical, as a physicist who works on optical tweezers, and who's essentially getting out these things, this thing called spin-orbit interaction, something which I had absolutely not heard of 10 years back. Or no, okay, 10 years back I had heard. 12, I am really senior now, I forget that. So 2009 I hadn't heard of it. 2012, of course, I had. But then we have grown in this, and now we actually do stuff which I am pretty proud of. Of course, we do not publish in Nature and Science and all that, but those are journals which have a big boundary, potential for Indians. And anyway, so I'm not going to that. But before I indulge into all the details of the story, I think it's important to talk about the people who are the heroes. I'm just there. So this is this infamous Orijit who started all this business. He's at SNMOS. This guy took the baton from him, Basudev. He's now an associate professor at IIT Madras. These three are MS students who all perpetuated, carried it on. And these two are sitting right there, and you can catch them and hit them till they squeal and tell you what they're doing. And they have posters out there. So I'm going to talk about their work somewhat. So they keep the momentum, longitudinal, transverse, both. And I also have a new student now who has joined, who is still too much of a fresher to be appearing on this. These two are the people who have helped, so we three are a group right from the first days. This person who just gave this really exciting, that you can create excitement by just oscillating here, is something that one should have been a witness to from what Subhasish talked. So Subhasish, Nirmalya, myself, this group, or whatever papers we have published, it is this group that has done it. And we are really complementary, because Subhasish is the person who really taught us how to get into this thing called, how to analyze our results, because we saw some things in experiments which were completely confounding. We had no idea what the hell was happening. It was not there in literature. Then I remember, I think it was in 2011 or 12, 11 I guess, we went to Hyderabad, and Subhasish saw the results, and we said, what do we do? And then he taught this chap this thing called angular spectrum method, and it was like, this Alibaba's thing, right? That open sesame. In Bengali we say chiching park. The thing just opened out from there. Okay, so anyway, before I go into this story, so our lab actually does a lot of other things. So I know there are people also here who are not really completely focused on this, but this is what we started out with. We were actually supposed to start with biology, but till date, I have done, I think, 2% biology of the 100%, if I consider all my research as 100. Okay, This is something which we are very proud of. We have developed a technique by which, so you saw here, this is written by a bubble. This is 2 microns. This is written IISER. We have discovered this kind of thing. Something we are working on quite a bit, StatMech, especially non-equilibrium StatMech, using this so-called thermodynamic uncertainty principle that has been very hot for the last 7-8 years. Again, something, this trapping in air, I'm going to talk about trapping, of course. Trapping in water is not so difficult because you have the viscosity to help you. Trapping in air is very tough because particles shoot about like bullets. You have to still catch them, and it's not so easy. We don't use high power lasers as well. There's no vacuum. This is something, again, we have just got into about maybe a year. Yeah, my latest student's PhD thesis is mostly on this, on waveguides, which we, again, these things out of peptides. And peptides are very important because Alzheimer's disease is made of some amyloids, which are peptides. And we try to see, couple light inside them and see some very interesting properties such as phonoresonances and cavities. We essentially make cavities out of them, both waveguides as well as just longitudinal cavities, Fabry-Perot. And we can see some very nice changes in the performance of these cavities, which helps us to go towards very, very high precision sensing of dyes and all that. So essentially sensing. Okay, that's that. So, okay, optical tweezers. So this incidentally got the Nobel Prize in 2018. The prize was given to Arthur Ashkin, and it was given specifically for his contribution in biology, which I don't do. I do very little. But optical tweezers are, the problem is, so they are something, so you know mechanical tweezers, right, which are there in any bio lab or anyone, just even, you can use them to pluck your eyebrows also. So you just have these entities, you hold them, you take small objects and move them around. Optical tweezers are the same thing done with light. Absolutely same thing. You take particles, move them around, and do all kinds of things. And you kick them, you can measure their response. And by measuring that response, you get information about their environment as well, where they are embedded in. So you can do something like force spectroscopy. You can apply controlled forces, and you can also measure the response to those forces, by which you learn about particles, you learn about the environment, lots of things. Unfortunately, it's used mostly as a tool because you can do so much, kill with them. But just in the process of focusing light, there are some extremely interesting properties which come out, which is what we also stumbled upon, and which is unfortunately not so popular as as using optical tweezers for pushing particles and pulling particles and stretching DNA and unstretching some cytoplasm, all kinds of things. In biology, the research is much higher than in physics. Yeah. So, of course, why optical tweezers are tweezers is that light can apply force, and that is well known. Photons have momentum. Light has radiation pressure in the classical way. In fact, the radiation, I didn't write this here, but if you go out, of course, it's not that you go outside and stand in the sun and you fall down. Of course, it's not that. But sunlight, I think, has a radiation pressure. If I remember the numbers, I think at full, the full sort of an afternoon or something, it's about 1300 pressure is what it is, extremely high. Some 1300 newtons per meter square or something like that. It's extremely high. But 1361, I think you can check this up. Importantly, that amount, so it will not, of course, affect a fat person like me, but if I were to be a 600 nanometer particle, I would get an acceleration of, I think, 10 to the power 5g. It is huge, enormous. And that is exactly what we use. That is exactly what we use. Our targets are, of course, very small particles, not atoms. The smaller the particle, the faster it moves around, and the larger forces you need to stabilize them, to catch them. Okay. So this is exactly what we use. Very importantly, however, if you just have light which is unstructured, which has no variation of intensity, then you cannot trap. Then you can just push. Then you can just exert pressure. There will be no trapping. This is the famous radiation pressure force. There will be scattering. If, however, you have some structure in the beam, you have some intensity gradient, then there will be a restoring force. And a Gaussian beam has that. Okay, so what is that? So consider this. This is just a cartoon. This beam is moving like that in the Z. Transverse profile is like this, right? And you have this small polystyrene sphere. Polystyrene, it's transparent. Refractive index is about, say, 1.56, something like that. And this is embedded in a fluid whose refractive index is lesser, say water, 1.33. Okay. So what happens is, I have, say, this light is whatever, it's coming like this. Okay, this is my z-axis, the light is coming like this. Then, because this is higher refractive index compared to the outside, just by plain refract, okay, so I'm taking a liberty again, massive liberties I'm taking. This is like a wave, but I'm saying, so this part is much higher intensity than this part, right? But then I'm just saying that suppose there are rays here and this ray is thicker than that. I'm representing the higher intensity in the form of a thicker ray. Okay, so what I'm saying is that this ray will refract like this, very simple. You draw a normal here and you will see that this will go towards the normal, right? Because you're going from lower to higher, right? So then, and then when it comes out, it will go like this. This one, which is much weaker, this will do the opposite, right? Now what happens is, now this has higher intensity, this ray is stronger than this. What there is, they don't cancel each other out. The effects do not cancel each other out. Okay, there is a resultant which is actually in this direction, but just so the light is shifted more towards this. But just by Newton's third law, every action has an opposite and equal and opposite reaction. The sphere gets a kick to the opposite direction. Similarly, if I go here, if this tries to go out, it gets a big kick, it goes here, it gets a kick in this direction. It will keep on oscillating, right? And it is very akin to a spring mass problem, where this is nothing but this part, this object. This is my spring. My tweezers is a spring, and what we have is a linear restoring force. And this is proportional, this is essentially proportional to the gradient of the intensity. How that comes, Subhasish tried to give it all out. I'm going to still repeat that, but I'm going to probably talk in more detail. So this is how it gets trapped here. You see there is, and that happens only and only because there is a gradient. If this were the same, you would have no restoring force. If this were just a flat beam, nothing would have happened. That is what you should understand. Because there is a structure in the beam, there is more intensity here than there, you get a force, restoring force on this object. Okay. So now can we try to understand this a bit more physically using the language of math? And this was the seminal paper by Gordon, 73, Physical Review A. And so I'm again advertising pretty shamelessly this book that we have written. And you will find this in chapter 13. This whole thing is, we have dealt it right from force on a dipole and all that. So this is this sphere, this object. This has a polarizability. That is very important. It's a dielectric. There is a finite polarizability. And if you know that if there is a dielectric, there's a polarizability, you will actually get an induced, there will be an induced dipole. If an object is a dielectric, there will be an induced dipole. And the force on that is given by this. This is a classic expression. Okay, this is derived in this textbook. If you want to look at it, you can get it. And then I can just, a little bit of manipulation, I get this. I write P essentially as alpha E. P alpha E means this is essentially this. This part, you can, again, this E dot del E, you can write, I think Subhasish showed all this in detail. You write this as this, and then you use the Maxwell equation, essentially get something like this. Okay, this is the Poynting vector E cross B. This is the crucial part. This del T of this Poynting vector is 0 because it oscillates so fast. Your measurement time scales are at best, at very, very best, maybe not even picoseconds. The best in class is something like maybe nanoseconds. This is at the speed of flight. This is frequency of flight, 10 to the power 14, very, very high. So this is essentially 0. We have this term left. And we look at this a bit more in detail. So if I have this is what I have, and I write E as like this, and E squared is this, then I get two terms. I get one which is directly proportional to this gradient of the intensity, and I get another which is the gradient of the phase. By the way, if you recall, this guy here, and I will come back to this, is nothing but this canonical momentum on which Subhasish dealt with it, in so much detail. This is nothing but this. And here also you can see that this is my gradient force. This is the derivative of the intensity, gradient of intensity. And here you have the gradient of phase. So what is gradient of phase in quantum mechanics? Del phi del x. What does that give you? Yeah? Del phi, yeah? Angular momentum, right? It's nothing but angular momentum. There's a phase gradient. In quantum mechanics, that is what we get, right? And that is why this part is essentially associated with the orbital angular momentum. This is the gradient of phase. We'll come to that in more detail. Typically, this is a destructive thing in optical tweezers because this will not provide any restoring force. It will just kick the particles away. Okay. Here, however, this is what really matters. Fortunately, in these spheres, these dielectric spheres embedded in water, these have extremely, so if I just think of these as reflectors, scattering essentially some kind of, any reflection is a scattering process. But if you think of it, because the gradient of intensity between the contrast of intensity is so small, this part is very small. Sorry, the contrast of refractive index is so small between a sphere in water, anyway a sphere, a glass in air, it is very, very small reflectivity, right? So this term is always much smaller than here. There is another term which I did not write, which depends. So this, again, one very important thing you can see here, this is polarizability has a real part and an imaginary part. So imaginary part is linked with this. This is with the real part. So with the imaginary part, you also have absorption. And that is a nuisance because that, again, heats up particles and that creates very large, the Brownian fluctuations and all, and they tend to leave the trap, right? But the scattering is a killer because it will just throw the particles out. And therefore, if you actually use, this we have seen, if you use wavelengths which are low wavelengths, then the reflectivity is higher typically of these spheres. It's a pain to trap. You try to trap at UV or at even blue, it's not easy. It is not at all easy. With the same power, you'll get no trapping. Okay? So this is now comes my story. And this is what we finally see. And this thing that we observed back in 2011 started the whole process. Because this was completely inexplicable. So what you have is a whole circle of, this is some kind of a garland of particles, all of 1 micron diameter, which are strangely assembling. They have no business to do this, but they are still doing it. And here, of course, you see a particle, this is sort of a longish particle, which is sort of trapped in this kind of another strange sort of light profile you can see. and this is just moving around it, and it's moving around because I am essentially changing a lambda by 2 plate outside. I'm changing polarization. I am not moving the beam. I am not moving the beam. This particle is moving. Here, this guy is merrily revolving around. This is very interesting. I'm going to come to this. You can see rotation. Then this rotation sort of suddenly stops. Yeah.
Do you make the assumption that the particle is smaller than the wavelength?
No, nothing, absolutely not. This is essentially me regime, completely me regime, not Rayleigh at all. This is bigger. This is me regime. Absolutely not, completely. So that I showed was a very, very basic thing. But for me, it is much more complex. It's not this. Okay, so this is what happens to particles. This is what happens to the light. This is crazy. I'm starting with a Gaussian beam, and look at the intensity pattern near the focus. A Gaussian beam, of course, this is a transverse cross section. This is how it should happen. But see, if I've started with spherical beam, it's become elongated. Look at this. It is broken into structures. I've done nothing, just focused. I've just focused. This was actually a Hermite Gaussian beam. Hermite Gaussian beam, you may know, that is the first, in simple harmonic oscillator, linear harmonic oscillator solutions in quantum mechanics, ground state is a Gaussian, first excited state is Hermite Gaussian. So it's like a two-lobe beam. So you see here, it was supposed to be these were like, expolarized. These were supposed to be like this. This has got bent. Here it's got bent the other way. This was, circular polarization, of course, but this was not supposed to be, this strange tilt was not supposed to be there. Here, this is even crazier, right? Because I have a Gaussian beam, and then I have completely strange patterns. This is not supposed to be like this. These are simulation results because it is very difficult to image things like this because imaging when you're trying to do, and I'm going to come to that, it is very difficult to select out that focal plane. You get effects from every single structure that is there in the problem. But even in simulation, you see what is happening. I've started with a beam like that, which is more circular. I've focused, and near the focus, I'm getting this completely crazy structures. You can see here, the symmetry is sort of broken because here you have higher intensity, here you have higher, here you have higher. It's all different. So essentially polarization, the input polarization, and other things also, the refractive contrast of my trapping chamber. Okay, so very, very interesting change in polarization also. I come in with right circularly polarized and I generate left circular. I come in with circular polarization. I come in with zero orbital angular momentum, but I get orbital angular momentum. This is strange. This is almost magical. And I always find light very magical. We just think of interference, right? It's like making darkness out of light. You have two bright beams. You just point them, this pointer, right? Nothing. Oh, sorry. Oh, man. This is jumping all over the place. This is completely bright. You throw another piece of light on it, it will continue to be bright. I block it, becomes gone. Then I break this light into two parts, and superpose one path on the other, you get darkness. There's no darkness embedded in this light at all. That is the basic thing, of course, because it's a wave. We all know that, but it is quite magical. And here also it's very strange, right? I'm coming with a Gaussian beam. I'm doing nothing. I'm focusing, and lo and behold, it becomes like this. And that light also makes these particles do these completely crazy things. It is spinning. This is with linearly polarized light. That carries no intrinsic spin. There is no intrinsic spin here. It's still spinning. Okay, so now we come to the main topic of this talk, spinning particles in optical tweezers, which is actually, well, now we think of it as some kind of a no-brainer, because you know that, so there's this famous experiment by Bethe, where he showed that you have a lambda by 2 plate, wave plates, I think I'm sure everybody is familiar here. You come with circularly polarized light, and you actually see the wave plate twist because it's sort of suspended by a very, very tiny spring. I mean, very thin string. So because there is, so you think of it as a birefringent particle, and you have circularly polarized light. So there is an exchange of angular momentum, and this object will spin, will twist. This is essentially Richard Bett's work, seminal paper in 1936. 1998, Helena Rubinstein Dunlop's group saw this in optical tweezers, where they saw this vaterite particle spinning using circularly polarized light. Exactly the same thing. Exactly the same thing. You come in with circularly polarized light, you have a birefringent particle, there's an exchange of angular momentum, spin angular momentum. So this is the talk. So this you see, this is, you have to look at this paper. This is a very standard expression. But this is essentially the term that is giving you the orientation of the particle with respect to the field of light, the polarization of light. So if you had linear polarized light, then you would see, and this theta is essentially the angle between your particle's axis and the light polarization axis. So if you come with linear polarized light, you will just see the particle orient with respect to the field. If you come in with circular, you see continuous spinning, because this is essentially the difference between the ordinary, the extraordinary and extraordinary of the birefringent particle. And this term essentially is the spinning torque term. And this was this was something which should have happened, and it did happen and became a Nature paper. So you are essentially coming in with light in this direction, and this is the z-axis. Particle spins like this, like this. Absolutely fine. This is nothing but the longitudinal spin angular momentum. As we say, LSAM, longitudinal spin angular momentum, expected, but still achieved in experiment, which was great. What I am doing, however, I am not coming in with circularly polarized light. I'm coming in with linearly polarized light. There is no spin angular momentum in the light. It has no spin. Yet it is spinning particles. And more interestingly, I am not only spinning particles, I am revolving them as well. And that too with zero input, intrinsic orbital angular momentum. I'm not using a Laguerre-Gaussian beam. I'm not using any beam that is carrying intrinsic OM. And yet I'm getting particles to revolve. And most interesting, what I'll tell you at the near the end of the talk, this spin is expected. That spin is not. This is just LSAM. But this or this are effects of transverse spin. And that too I'm generating by just, here we didn't use just a Gaussian, but even with a simple Gaussian beam structure with, of course, that for transverse spin you do need LCP, RCP, that is left or right circular polarization. But you do not need, we have actually shown that you do not need an evanescent wave. You can generate transverse spin for propagating fields as well. And that happens because of this. So spin-orbit interaction in atoms, of course, I'm sure you're all physics students, you've certainly read, because that is finally gives atomic structure. Because the Bohr theory said that it is just all principal quantum number. That is not correct. The hydrogen atom fine spectra prove that. By the way, atomic physics is one direction where absolutely everywhere experiment has preceded theory. Everything. First experiment has been done, then theoreticians have, just sort of pulled their socks and tried to make a theory for it. Fine structures were seen first, and then it took many, many theoreticians of the stature of, Sommerfeld and Bohr and all to finally come up with the solution to kya ho raha hai. So there you had, of course, electron spin, electron angular momentum, orbital, that is L, which in the classic theory of Bohr, initial theory, that does not manifest itself. L is not there in the energy. There's an accidental degeneracy. This does not manifest in the energy. But the moment you have spin, when it was known there is this intrinsic quality called spin, you have an LS coupling, degeneracy is lifted, you have fine structure, you have high fine structure, you have all kinds of things. There is an energy shift because of LS coupling. What happens in light? In light, what happens is, because of this interaction of the spin and orbital angular momentum, you have very interesting polarization dependent trajectories, interesting intensity distributions depending on a particular polarization. Beam shifts, which we call the spin Hall effect, orbital, and the Hall effect, which can be both orbital and because of the spin Hall effect and the orbital Hall effect. So what really happens? What really happens is this. So this I will steal from Konstantin Bliok. So what he had said was, if you just think of, so there are two types, right? There is this K vector propagating and the electric field polarization, which evolves as per the trajectory. So you just think of this. This is my K vector. This is my electric field. Okay, and I just do this, I do that, and I do this. I've done nothing. This has been shifted by 90. Start like this. Do this, do that, do this. As my wave evolves, K vector goes through, my polarization just rotates. That is called spin redirectional periphase. The other, so I have this, so this is all a matter of some kind of geometric phase. We'll come to that. There is the other thing, which is called the Mancharatnam Berry phase. So what we have here is interesting that, of course, this is what I said, that the field, the polarization vector evolves. Here you see that I start out with, from the same origin or something, one LCP and one RCP, and as they propagate, you see there's a transverse shift, there's a shift in trajectory. Okay. So how is this seen in optical tweezers? Or rather, okay, let me just, before that, oh yeah, so this is the spin Hall effect, as I just want to maybe just a few lines on that. Shift of, as I said, orbit, just the transverse shift because of your polarization dependent. There is the orbital Hall effect as well, where you have opposite angular momentum modes, or OAM modes are shifted spatially because of input your spin polarized light. So all this happens because of a geometric phase. Some kind of geometric phase is involved. What is happening here, you know that orbital, any kind of L, comes from a del del phi. There has to be a gradient of geometric phase somehow, of phase. Some phase gradient has to be involved. Some phase gradient. L is connected with some del del phi. How does that come? So before that, how do you understand geometric phase? I mean, there are things of, some kind of, complicated, not complicated, where you have, say, closed paths of trajectory and whatever, all kinds of things. I have a very simple way of understanding, and I just want to share that. So I can just write my E as some this, right? Perfectly simple, plane wave. Everybody knows. How do you get any kind of dynamic phase here? Dynamic phase matlab, right? But when you do what you do in an interferometer, Fabry-Perot, Michelson, Mach-Zehnder, whatever. You take a beam, you go two different paths. There is a R2 minus R1. You get a phase shift there. For me, geometric phase is that you don't change this, you change this. The K vector, it can differ. This to me is the spin redirectional. There is the other thing, which is this guy, I can write if phi is 0 or pi or 2 pi, this is linearly polarized. If it is pi by 2, it is circularly. Other angles, it is nothing but elliptically polarized. So that I can represent, if I just now change this, I essentially, I go through a trajectory in the Poincare sphere. And that is my Pancharatnam Berry phase. And this is nothing but the spin redirectional Berry phase, where I change just K, here I change the direction of E. This is a very simple method. See, I'm an experimentalist, I search for simplicity. This is what I try to use to understand this. Okay, so now the moment you have, and so this is there. The other thing that is very important for observation of any spin, orbit effects and all, is that you need a z component of light. We know from the paraxial approximation in the plane wave picture that light goes like that, k vector is like this, E is this way and that way. Plane wave picture can be nothing in the z, which is straight wrong. Why is it wrong? This is correct for plane waves. Plane waves, it's fine. But the moment you have a boundary, you have a structure, immediately, because you know that this has to be satisfied, this is satisfied trivially for plane waves. Because they have no the intensity is independent of field. It is just, the fields are constant. Intensity is E0 squared, mod E squared. Everywhere is same, infinite extent. The moment I put a boundary, there's a transverse boundary, right? This has a boundary. This is not a plane wave. That means Ex and Ey are bounded. So del dot Ex and del dot Ey will not be 0. So just because to satisfy this, you have to have an Ez. And that, when you actually increase, focused light very tightly using what we do in optical tweezers, a high numerical aperture lens that is used in microscopes, aperture of like 1.4 or something. We have 1.4, 1.3 typically. Now you have actually objectives of 1.6 even, extremely costly. So that is basically numerical aperture is a sign of the angle of bending. The more the bending, the higher the NA. But the more the bending, the more is the variation of Ex, Ey, the more is the variation of Ez, or the generation of Ez and the variation as well. Right? So importantly, as we will show, there are many nice ways of manipulating particles using these. So what we are doing actually is using these particles as probes for observing effects of spin-orbit interaction of light in optical tweezers. These are just probes, and also we get some extremely interesting and very, very complex manipulation of these particles. Right? Okay, so this is what we have. This is the experiment. And this is like every single optical tweezers will work like this. You have an objective lens, very high whatever numerical aperture. You have light coming in from the bottom. You have a sample chamber, and this is where everything, the fun starts. Sample chamber, this is just a slide, microscope slide. Everybody has seen one. Cover slip. You have sample inside. What is sample? Typically, we take just water inside. We put in some polystyrene beads, whose beads are the spherical, beads. Maybe about 1 micron, 2 micron, 3 micron. The lowest we have got is about 0.6, 0.5. We have 100 nanometers as well. But you cannot, of course, trap them individually because diffraction limit bars you from seeing a 100 nanometer particle. So this is what happens. So you come in, with light microscope, this objective focuses this very strongly inside. By the way, this thickness is very important because this working distance of these objectives will keep on falling as you increase the numerical aperture. So for example, this one at 1.4, this will have a working distance about maybe about 200 microns. So I cannot have this, or not 200, about 300 microns, sorry. So I cannot have this more than about 250, right? Typically people use about 160. That is the thing that is available in markets, most common. You can buy, I think 100 rupees, you get some 10. I mean, you get a packet. It's very, very cheap. I think per cover slip is some 10 rupees or something because it's used widely in bio. Okay, the thickness of those is about 160. Importantly though, the refractive index of those cover slips they are glass, right? Now, if I want to get a numerical aperture of 1.4, I need to put something here. What is that? I need to put immersion oil. And the reason is that in air, I can never get my sine theta, the n sine theta is numerical aperture, right? Sine theta can never be more than 1. N sine theta is numerical aperture. So if sine theta cannot be more than 1, how can I get Na more than 1? So therefore, I need a small n, that is refractive index, which is higher than 1 or whatever. That is why you need a immersion oil. But importantly, everybody before actually we started doing experiments use the same refractive index of oil and this cover slip. And the reason is easy to understand. If you have any refractive index mismatch, because of your Fresnel conditions, the beam will get distorted. Most importantly, the beam will probably get bigger because of something called spherical aberration. And if the beam gets bigger, what gets compromised? By intensity. Intensity is powered by area. Beam gets bigger, then intensity will get small. Trapping force will reduce. Everybody uses the same refractive index of this and that. We don't. And we don't do that because I had no understanding of optical tweezers when I started out. This is one of the greatest examples of serendipity in my life. Because I was, we are situated not in Kolkata. We are situated about 50 kilometers from the airport and actually 70, 80 kilometers from main Calcutta. And it's not easy to get cover slips like that. And it's not easy to travel as well. And in 2010, 9-10, it was even more difficult. So you would rather want things to come to you than you go to, scientists want that, experimentalists want that. So I was searching for cover slips and I was buying these particles from Sigma Aldrich. And I saw that Sigma Aldrich also sells cover slips. I said, wow, brilliant. I mean, there are these beautiful plastic cover slips they are selling. Great. I mean, cover slips are cover slips. Because my ignorance was so much that time, I said, cover slips are cover slips, so let's buy. And I bought. And then I saw, Arijit, Shombit and me were trapping, and we see things like this. I said, what the hell, yaar? I mean, why is this happening? Because this is not reported anywhere. Absolutely not reported. I mean, what we are doing is, we are doing nothing. We are having a linearly polarized Gaussian beam. We are coming, we are focusing. And instead of particles being trapped in the center, they are forming a ring. And this ring is becoming bigger and smaller as I change the objective focus. We were completely intrigued that why is this happening? Why are they not clumping together? Because you would find, Gaussian beam, all the intensities in the center, particles you can trap multiple particles depending on the size of the focal spot. But they will be clumped. Why should they be beautifully trapped like this in a ring? So then we get all kinds of rings. All kinds of rings, different diameters, particle in the center, particle not in the center, different objective lenses. This was a Indian objective, 2,000 rupees, 1.25, 2005. That's why this picture is so bad. Of course, you give some and take some, right? This one is by Zeiss objective, 1.5 lakhs, 2 lakhs, 2,000, 2 lakhs, ring. Both were in the same paper. So, but the moment, so then we were totally perplexed. Kya ho raha hai? And then to increase the perplexity, we saw that when we use those glass cover slips, it becomes like this. All a big bulge of mess of particles. No ring, nothing, gone. Then we start, magical cover slip kharid liya. You put this cover slip, it becomes a ring. You buy a glass, kuch nahi hota hai. It was completely crazy, right? Ye kya ho raha hai? That is how now we are doing transverse spin, all these hi-fi things. That time you were like, ye mala or no mala? What is happening? And this is what I showed. I remember I showed this in a SPE conference at that San Diego. And this guy told me, impossible, you are doing, also what structured beam are you using? Are you using LG, what, Bessel, this, that? I said, nothing, yaar, Gaussian. Then he said, then what are you doing? This is PRL, this is nature. बहुत कुछ बोला. Finally PRA हुआ. Okay. So then I told him, see, I'm getting these cover slips which are 300 microns. Well, हो ही नहीं सकता. No, he didn't say in Hindi, of course. Italian. He said it's impossible. Impossible. You cannot trap with 300 micron cover slip. Impossible. 250 micron cover slip. I said, I'm trapping. He said, no, it will not. The light will not go through. I said, then how am I getting this? If there's no light going through, how am I trapping these particles? That was the ignorance. They think they know everything, right? It is nothing. The general thing was you only can trap using glass cover slips, nothing else will work. Okay? So what you understand is, this is the problem. This is the basic schematic. I'm coming in with linearly polarized light, objective lens. There are 4 different refractive index layers. This is the oil, not drawn to scale. Cover slip, sample chamber, top slide. This is actually badly out of scale. This is about 10 micron, 5 to 5 microns. This is 160 to 250. This would be about 20 to 30. This is infinity. This is 1.5 mm. We don't really consider this thickness. To all intents and purposes, this is infinity. Okay. So then, so we ran to Subhasish da, to Hyderabad basically. We didn't run to him knowing that he would give the solution, but we went to Hyderabad for a conference and we explained everything. Then what we realized that the only way out was to understand what the hell the field looked like. Because imaging is not a solution, because imaging will give you contributions from every single optic that you have. It is, unless you do confocal, that is also going to be difficult because you're not having probes that way. You just want to get the field. That in this region, how it looks, you can never swear that what you're getting is indeed exactly that. Because every other thing will also contribute. We did get some different structure though, it is there. But now you have to know why. Why is it coming to this structure? And that needed modeling. And that modeling, that whole thing, these observations started this field of research from which I have sort of 2 PhDs and maybe 3, 4 more and several MS students, and probably is growing, right? So what is happening really? Okay, so first things first. Okay, I'll probably not show this because otherwise you just look into this and not look at me. So what is happening is, you have to understand that this is the problem. Paraxial approximation will not work straight. Does not work, right? I have to solve the Maxwell's equations in their entirety. I cannot use any approximation that the second derivative of del square del z square can be thrown off. All that I cannot use. So what do you do then? This is what Subhasish Gupta told us. There is something called the angular spectrum method. And what is that? So that essentially is that you take your field, input field, go to the Fourier domain, write it as plane waves. Take each k space, k wave, propagate it by in the z, put a phase factor, inverse Fourier transform, again build the new field. At each z, you keep on doing that. And importantly, you keep track of polarization, because that is crucial, because you have interfaces now. And if you have interfaces, they have very, very interesting properties. There is TPTS and TPTS, that is the parallel, and the P is parallel polarization, S is perpendicular. TPTS are imaginary. That gives you straight a phase factor. So it's all linking up, right? Phase factor means there is something. What is that? That is the clear geometric phase. And why is geometric phase coming just by focusing itself? Because every k vector, this is the k vector, right, initially. Moment you focus, the k vectors have different trajectories, right? Of course, the magnitude of k doesn't change, but the direction will change. And they are bending differently. And the moment you do that, that means if they bend differently, there's a different phase. If there's a different phase, there's a phase gradient. If there's a phase gradient, there's orbital angular momentum. So if you have input spin, you generate orbital angular momentum just by focusing. And this geometric phase is what we are tampering with the moment we put interfaces. And when we put interfaces of different Ri contrast, the geometric phase completely becomes, evolves in a very, very different manners. And that generates everything. You now also, because of this tight focusing, you have a Z component. Because you have a Z component, your pointing vector is no longer longitudinal. There is a transverse pointing vector. That means there is an Sx, Sy, there is straight, you have a spin momentum. Because finally it's the pointing vector which gives you both, the canonical and the spin. Right? So this is what we are doing. You take the initial, this thing, you basically, this is the initial field, Fourier transform, go into K domain, propagate by this phase factor, reverse Fourier transform, get back. This is very easy to see. It is very difficult to do because the next equations I'll show you, you'll want to run away. Okay. So here they come. So what I'm doing now, I'm basically focusing, and I'm taking the focusing as just a rotational transform. A series of rotation matrices is what I'm emulating my act of focusing. So I take, this is say my initial K wave, I'm going to that, right? So I basically do three transformations. I change by phi, go to change it to theta, go back to lap frame. So I go to the ray frame or the K frame by phi, theta, azimuthal, then my polar, then minus phi, go back to lap frame. So essentially my input is, this is my resultant, this is my input incident, this is the rotation matrix. And here you have,
Did you put Wolf's paper or this Monroe's paper reference somewhere?
Wolf paper, I forgot. Yeah, very bad mistake. So Richards and Wolf has this seminal thing. So this is where we took all this from. It's a bad mistake. Absolutely. No, I completely forgot. So I should have put, it was there in the slides. I by chance just removed that thing. So this is Richards, Wolf. There are two papers in optics communication in 1958. Optics communication. It has an impact of 1 point. No, those two papers in 58, that was in Royal Society. Acha, then my mistake. Okay, my bad. There is an optics communication paper also, no?
No, that maybe might be later. But
Later. Royal Society, there are two papers. 1958, those. Okay, that was in Royal Society. Yeah, so I just, yeah. But optics communication, there is a paper. I'm sure there is a paper. That is much later. Okay. So anyway, so yeah, I totally forgot that. Sorry for that, really. But yeah, so I can tell you. You can. Yeah. I will tell you when you come to me. I will just tell you. I have the papers. I can give them to you as well. I can put them on the drive as well in the TIFR thing. So anyway, so what you have is this. These are my contribution of the my polarization contribution of the interfaces. And finally, you do all this and you write. You get this A, B, whatever, which are just functions of this TPTS and all. Then you remember that Kx is this, Ky is this, Kz is this, X is this. You go to cylindrical frames. And then this is the final expression you get. Okay, so this is the final expression you get if you put all this. Now remember, this is just my E, so I actually will have to finally go to the resultant field where there is a matrix standing in front. And if I just write down these integrals properly, try to solve them, I essentially get these diffraction integrals. Vector, this is pure vector diffraction. Okay, I get these diffraction integrals where what I finally write, so basically what I've done here is this, I have incorporated with here, we have take these, and finally we write everything like this. This is a matrix, this is my polarization input state, okay, and this is the final polarization, final field. Okay, so everything is written now, so this is Ex, Ey, Ez. So the thing is, the formalism is not difficult. The execution is extremely complex. Formalism is just Fourier transform, and remember the limits of integration are important. Your phi goes to this. Theta max is defined by your numerical aperture. Okay. So There are some other things I did not put. So there is something called apodization, which you have to remember, because when you go from ray frame, which is like, plane wave, it's a plane wave, and then you go to spherical wave, that's a different thing, right? So you have to apply this pupil function. So that is all technical detail. If you can look into our papers, it is well explained. In fact, Origin's thesis is like a textbook. It's an MS thesis, but it's like a textbook. Okay. So anyway, so finally you come to this. This is what I finally get for input linear polarization. Now say I put input circular polarization. Okay, then this will be say 1 I0 or 1 minus I0. So then I can actually, so then I get something like this, right? If I had 1 I0, then I can actually break this down into the constituent other circular polarization as well. I can basically write my input, suppose it's 1 I0, I actually will get a 1 minus I0 and this longitudinal component. This is all writing a matrix like this, a vector like this, in this form. And you can, physically you can understand this, right? Because there has to be an orbital angular momentum. If there is an orbital angular momentum, then for conservation of momentum, you need the opposite spin. You need the opposite spin. That is called spin-orbit interaction in this case. Interestingly now, if I actually come with linearly polarized light, I actually get both. I can now break down this into all kinds of different things. Conservation has to be kept in mind. So input linear, I actually get regions of LCP, RCP, I get longitudinal component. And that becomes very interesting because if I now do this kind of this is actually looking at, the helicity, the Stokes vector thingy, then you can see this is the extent of circular polarization. Then you can see that I have, this is blue is, I believe, positive, this is negative. Yeah, this is minus actually, you didn't write. So yeah, so you get regions of negative and positive and spatially separated, transverse direction separated. So if I actually put a particle here, it will spin one way. If I put a particle here, it will spin the different way. Right? And this is exactly what we get. You can see that this is spinning this way. They're very bad videos, and I've switched on the light. You can see that's at the edge. If I switch on the light, you see it's at the edge here. This is another particle spinning completely the opposite way. No, linear polarization anyway you'll get. No. The only thing that we do is have a cover slip which is different refractive index. Yes, that is very important. That is very important. So that refractive index ka contribution is actually making this focal spot bigger. So this thing which I have not told you here is actually taking it not at the focus, but 2 microns away from the focus. So when you have a mismatched cover slip, you actually get an increase of the focal spot diameter. And if you go higher, that even gets more, so that it is possible for me to place a particle here. If all see this extent, this is 4 microns. This is large. If I actually have a 1 micron particle, I can selectively place it here, try to place it here. These are, of course, opportunistic experiments. You cannot just take it, you cannot will them. You try 10 times, it will happen probably once. Ramanujan will tell you, try 1 month, it happens once. He doesn't do it well, that's why it happens, that rarely. But generally, these are opportunities, these are not easy. Okay, so spherical aberration, this mismatched cover slip, what it does is, it makes the focal spot bigger, and we also see at 2 microns away from the focus. So then you are actually able to access these different spin zones and put particles there. Put particles when the particles go themselves there. More interestingly, what happens if I have 2 of these beams? If I have 2 of these beams next to each other, then you see this is sigma minus, that is sigma plus, right? And if I can merge them, I will basically cancel out the spin of this with that. So in principle, I can have a particle which is spinning, then I can shine another beam and make it stop. This is what it's doing, it's spinning. It's a quartz particle, stopped. This is the second beam. Stopped. Again, let it go, again it's spin. So this is a very, very nice example of actually engineering the spin of particles by using these two beams, or purely using this kind of spin Hall shift effects. Okay. So this was published a long time back, 2000. Okay, this was 2013 or 14. See, I forgot to put the date. Anyway, I can tell you, I'm here for the next 2 days. So yeah, so then the next thing was different, and again, this was preempted a lot by Subhasish, so I'm not going to go into too much of details. But we moved on somewhat from here to see other effects. So this was input linear polarization, remember. What happens if I put input circular polarization? That is interesting because circular polarization means there's going to be a very, very strong orbital angular momentum component, right? And what we wanted to see was there was this general thing, desire to see effects of transverse spin and all that, but this Belinfante was appearing very interesting. And again, what happened, of course, see this case, experiments preempted our simulations. We actually saw that ring structure happening, then we unraveled and we got all kinds of things, and we therefore did this. Here, my MS student basically had put in a circularly polarized beam. And remarkably, he had seen particles revolve, which is not expected. I'm not putting any angular momentum, orbital angular momentum. It's a Gaussian beam. But with spin, and it's revolving. It's interesting. So then I said, okay, so what happens if you reverse the circular polarization? Intriguingly, the direction of that revolution is changing. So remember, so what I think has been discussed in length, the Poynting vector has two components, right? One is the OM, that is the canonical part, PO, and there's the spin part. The canonical part does not have any dependence on input helicity. But here, I'm giving LCP, it's spinning, it is revolving one way, I'm giving RCP spinning the other way. How? It should not. It should be independent of helicity. Again, we tried to solve, and we came up with a very, very nice understanding story of what happened, what is probably happening. And that was basically a signature of that elusive Belinfante spin. So spin momentum locking in condensed matter is very well known, where you actually have these, these charged surface states spin locked to their momentum, well known in condensed matter. Here what you have is this helicity dependence of rotation, of orbital rotation, basically of the Poynting vector. So again, this is something, by the way, there is this very, very nice paper, again I forgot, this should have come. There is this very, very illuminating paper by Konstantin Bliok. It's called Extraordinary Momentum in, what is that? Extraordinary Spin and Momentum in Evanescent Waves or something. Nature Photonics. Nature Communication, I think 2015, I guess. I have that paper, I'll just give it to you if you want it. So he broke it down. So this is again well known. This is the canonical part. This is phase dependent. Belinfante put this part. This is just emulating the quantum mechanical understanding of spin. And very importantly, again, as Subhasish said, this cannot do any work. You do del dot, this will become zero. So the the Belinfante part is not capable of doing work. So then one interesting question is, even for plane waves, so how do you say that there is a spin angular momentum? How is it there? Right? You say that is sigma z, right? So how does that spin angular momentum come if this is incapable of any work? So because that spin angular momentum, we know that can revolve particles, right? It can rotate particles. We have seen that. It is known. So that explanation is nicely given, that understanding by Bliok, is that this essentially means there are these local spin loops. So for a plane wave, if you consider infinite extent, they will all cancel out. But the moment you consider a boundary for any Gaussian beam or any structured beam, there's a boundary. The boundary current will not vanish. Or even for plane waves, if you consider along the z-axis, there will be a sigma z. You will have finite spin. For any structured beam, of course, there is a limit, and in the limit, the spins will not cancel out. So you will get effects of your LSAM, right? But very importantly, this part, canonical part, does not depend on input helicity. This part depends. This part depends. But it does no work. So how do you see it? Evanescent waves, there is literature, people have done it. In fact, when we sent this out for review, comments came that this has been shown. We said, we know it's been shown, but it has not been shown for propagating waves. Of course, that went to deaf ears. Anyway, so what we saw was this is E cross E star is the well-known, and H cross H star as well, the democracy, electromagnetic democracy was what he was mentioning. So if you take this, and if you go by that formalism that I showed before, then these are some expressions. These are very big expressions, but you can work out the math, algebra. But what you can see is that Sx and Sy do not change sign for RCP and LCP. Sz does. Px and Py flip signs. Pz doesn't. Right? So this part, this is the pointing vector. This is the entire pointing vector, E cross H, entire. That's split sign. And that is basically because of the contribution of the Belinfante spin. Right? So this is how, if you look at a quiver plot, if you plot it, you see that here, this is basically Px, and this is for LCP and RCP. This is essentially that way. This is essentially this way. So the simulation nicely shows it. Experiment. JAS experiment show. So again, if I do some simulations, what I see that this is my intensity. This is where my mismatched cover slips are so useful. See, this is my intensity profile. These here are my pointing vector. These things in this, these lines here in faded, in weaker colors. So you see that this is my total intensity, but my peaks are here. Look at this extent. It is not even a micron, this total thing. I use a higher cover. This is 2 microns beyond focus. At focus, it's worse. So where this is high, when my transverse spin is high, this is already low. Already low. And here it's gone, nothing. Here it's high, it's almost nothing. So you will not see any effects of transverse spin, of transverse pointing vector here. Right? But look at this 1.659, cover slip, I've changed. See, side lobes have started coming up. And here, this is both high, both are maximized. But look at this case. So high is my transverse, is my pointing vector, and so high is my intensity. So obviously, I will use this cover slip. And this is what spherical aberration does to you. You are actually getting areas, localized areas in space, where these interesting effects of polarization will be present even when there is high intensity. And this, yeah.
So you can change the liquid that you put in the index match.
That is also you can do, but the range is not very high. And for example, 1.8 is not easy to get. You can change, but again the thing is, Nirmal, those amount of liquid is very little, and liquid is it's not going to stay, right, because it's transient. You put it, it'll just fall off. You cannot put 100 microliters. You can maximum put one little drop, 10 microliters. It will change very little because the depth of thing is very important. To get higher effect, you need thicker. So liquid is not going to work. So this is again not so useful, but what I want to show.
Sir,
250 microns.
and the one that you're, let's say, you're using from a normal vendor. So is a difference in thickness or is a difference in
refractive index? So okay, that I did not say. So cover slip that I got from Sigma Aldrich was 1.58. 1.5725 or something, 1.572, sorry. Even that little gave me these strange effects. It was not 1.5, it was 1.57. And that was completely accidental. I had no idea it was that. We went and measured that in Calcutta Institute, CGCRI, and it came up to be 1.572. But then now we have a supplier in Lithuania who gives us a wide range. So this is basically what is interesting is I have a lambda by 4 plate. I have a quarter wave plate which makes circular polarization. Okay, and this is what I get. Very clearly, I get revolution in one direction, opposite. Negative torque. Negative torque, I mean, unless you have, see, I mean, but, oh, you're saying that you have, but see, this direction is as per my input polarization, so is going the same. But that is a very nice question that Ramanujan can tell you, that we have seen that when you have, this is a different thing out of context a bit, but when you've taken HG beams with circular polarization, then in the two different lobes, we are getting opposite motion. That is clearly negative torque. So that is not, I'm not discussing it today, but. Huh? Sorry? Janus to nahi kiya. That is we don't have here. You give us some, no? Yeah, absolutely. I mean, see, Janus is something I desperately want. Anyway, that should not be discussed here, outside. I know. Very little. Polystyrene. So, by the way, we use a wavelength of 1064. That is the most common wavelength for tweezers because biological cells don't absorb. Body doesn't absorb. And polystyrene at 1064 is nothing happens. Absolutely nothing. That will get hot. Metals are notorious because they will produce bubbles. Pawan will love them. I also love them, but in a different context. But they become nuisances for trapping actually. But that is another, so I think we were discussing, I think Nirmalya was also discussing the effects of transverse spin on absorption and all. That is a different thing. Heat. Oh. Okay, so I think, Pawan, we need to connect Ramanujan's work because there are very similar things we are seeing on liquid crystals. Very similar things. Very similar things. This is another discussion. Okay, so our rest of the day is done. Anyway, so could this be a scattering? See, because why this scattering has come is because we have actually seen that if you put these sort of strangely shaped particles, not symmetric, asymmetric particles, actually in this spherically aberrated field profile, they start rotating, revolving like this. They start revolving. And the reason there is that because the scattering itself produces this tangential force which keeps on nicely changing as the particle moves along the spherically aberrated, the ring. And it's a beautifully conservative force towards the center. So is it this? It is not, because the moment I take away the lambda by 4, it stops. Scattering cannot depend on that. It's very clear. Okay? So orbital part cannot be responsible because it will never change sign, right? So then the question comes, this I think Subhasish has forced us to do, if you change the quarter wave plate online, you're doing the experiment, you change it, what will happen? That's a very nasty experiment because remember, when you cannot have a quarter wave plate which will magically go from lambda by plus 45 to minus 45, right? You have to change it. Problem is the moment you change it, you go to elliptical polarization, right? Input. And that you do, that intensity profile gets completely changed. But if you had something which would go, okay, plus 45, start, switch, minus 45, that would be great, but that doesn't happen. You have to rotate full. But what we actually saw was if you do this, see, this is clearly reversed. So there's a particle trapped in the center. Along the side, this is sort of wobbling around, moving like that. See, this is going the other way. Clearly, this is going the other way. This is going this way, this is going the other way. But interestingly, this is probably spinning. So what we thought was basically if you change the quarter wave plate, you actually are also changing the LSAM. right? And those areas in my sample chamber, if you as a function of z, you have both TSAM and LSAM on top of each other. So if you go to another small, different region of space, you are probably sampling LSAM more. So here, this one you put.
See all these spinning pictures and this all your data, whatever you have, experimental data. Could you estimate the magnitude of the
No, because essentially means that you have to do a scattering calculation. We have to do the Maxwell stress tensor and all. No? That is Shobik's next job. We have to do the tensor. We have not do it. No, can't now. We have not developed that algorithm yet. You can do it, but once I think he's on that.
I think you are trying sometimes at Maxwell.
He started. There's flooded. He started. There's a lot of Anyway, so another different discussion. Anyway, so clearly, even by changing the quarter wave plate, you are seeing signatures of this thing changing. I mean, this is probably more spin driven than orbital, but something is happening. Okay. So this was the story here, and clearly this was a signature of the Belinfante spin, because it itself cannot do work. But the fact that I'm actually getting different trajectories by changing my input helicity, trajectories of my OAM, that can be only because of the spin dependence, the spin part of the Poynting vector. Okay, so this was there. Now the other question, last part, there is a fourth part, but I don't think I'll cover that. That is, can we get pure transverse spin manifested in optical tweezers? Pure transverse spin. Can we see? Because Sx, Sy is there. It's just E cross E star, Z component, E cross E star, there's H also, X component, E cross E star, Y component. That will, so basically Sz is this, just like that. But this or this, can it be seen? So a very recent paper in Nature Photonics by again Helena Rubinstein's group actually have shown this, that if you come with two opposite circular polarized light beams, then if you see here, so essentially this one and that one, now the Z components, that is Sz, is like that and like this for each. And if you actually co-propagate and coincide them, the Z component actually will vanish. So you will be left with XY. So this is a clever trick, though I think there are issues, because exactly cancelling off the Z component means the angle has to be exactly same, intensities have to be exactly same, and I would not be completely sure that you can do it, because it's an engineering problem, and getting completely perfect alignment I think is impossible. And I'm sure if we had done this, this would be maybe Journal of Optics. But anyway, so I think this is, there is however a much more elegant way of doing it, and that is by using a radially polarized light, radially or azimuthally polarized light. So what is radially or azimuthally polarized? LG beam with zero topological charge. Just R is 1. So you know the LG solutions, the ground state is Gaussian, but you have this laggard RL, this thing, right? RL e to the IM phi. So L is R, that is 1. So it's still a profile with a 0 in the center. Okay, topological charge is not there. E to the IM phi, M is 0. But R to the power L, L is 1. What is very interesting there is a Jones vector for such beams. It's cos phi sin phi radial minus sin phi cos phi azimuthal. So then E cross E star Z will be 0, right? Because it's just cos theta sin theta cos theta 0. So any spin you have is purely transverse. It's purely transverse, right? Because Sx, Sy will not be 0. Because you have Z component coming in, and which is finite by tight focusing. And of course you have Xy there. So if you see any kind of rotation in these particles, it is only transverse spin. Right? So this was a very nice thing that actually Ramanujan came up with. And these are the statistics, just in a nutshell, that in radially polarized you have ER, EZ, H phi not 0, azimuthal HR, HZ, E phi not 0. So the SAM, spin angular momentum, is this. And interestingly, this part So this is an experiment where you actually can tease out the effects of electric part of the field and magnetic part of the field differently. So the radial part expresses the electric part, electric field. The azimuthal part expresses the magnetic field things. Because in azimuthal part you have HRHZ0. Finite. Right? So you can actually design these two beams and get transverse spins effectively due to the one case the component of the electric field component, other case the magnetic field component. Right? And that is what we have. So this is again in a nutshell. This is a Z. You are looking at these parts. So this is the azimuthal, this is the radial field, how it goes as polarization. This is the azimuthal field. And you have a particle here, you expect spin like that along the x-axis. Right? So he has plotted all this, and you can see again that this is, so in the magnitude are same, ESAM and HSAM. ESAM because of electric and magnetic, they have to be same. You see, interestingly here, these are the intensities. Again, if you see this black one is for 1.814. You see there's large intensity here and there is large SAM here as well. Okay. And what we have seen is, I have to play it now. So you see here, this is spinning in a strange way. If you see this, this is essentially these liquid crystal particles given to me by Surajit. And you see, we are doing this is like a cross-polarized thing that we are seeing. These are polarization lobes, and this is stopped. Oh man. So if you see, it is actually going like that. If you see carefully, the lobes are like going like this. It's not going like this, certainly. It's moving like this. Right? And if I take this thing, if I take the time series, and if I do a Fourier transform, I see that this is power spectrum. I see this is like where it peaks. Now, if I look at this other one, this is for azimuthal. See, it is clearly going like that. Oh man. See, it's at times it is just not continuous, but this video stopped. Oh. This is the problem with. Yeah. Again, if I play. So you see this going like that. So this is pneumatic. So basically with just birefringent particles, we don't see this. These are these special liquid crystal things that Surajit sent. And what here you see that this is actually faster also. You see that this is about 3 hertz frequency. So why is this faster? So then what we saw is, we look again, Jivan helped us, that if you see the mean scattering modes, then this is the AN cross section and this is BN. So you see BN actually has some peaks around 670. So if this has peaks, so obviously the coupling with the azimuthal part is stronger. Whereas here this is unstructured almost. So you see here, you can, I think, I don't know how visible this is, but that we have to have, this is a work under progress. So we have we found that Q factor? I think we found, no? Order of not too high. It's not too high, but and azimuthal to the BN mode. But here what we are seeing is BN is probably having some structure, so it has some resonances, which means that this will probably spin faster, but I cannot. See, I made it loop, but somehow it just doesn't loop. So if you see this is going like that. Okay. So this was really cool because you're actually finding out effects of electric part of the TSAM and magnetic part of the TSAM separately. Okay. So this work is still under progress. We have not written this up. This is completely hot from the oven, and I'm actually done. Just a little thing. Okay. I'm not going to talk about this in detail. Shobik has a massive poster outside. I'm not going to steal his thing. Ramanujan also had his on that. But so, is there some other way that you can generate TSAM? And the answer is again no, without using Gaussian beams and all, nothing. And that's a very clever way. Again, this was totally suggested by Subhasish, is that you tilt the interface. If you tilt the interface, that straight breaks the phi symmetry. And most importantly, because you're tilting it, there's a cos phi factor which comes into the longitudinal part of the spin angular momentum. So cos phi factor, it will reduce. So burst by energy, just by energy conservation, TSAM has to increase. Right? There's a cos theta factor. Cos theta factor means the Z component gets changed, so the LSAM gets reduced. And clearly, TSAM gets enhanced because of conservation. And what Shobik showed is that you actually have an angle at which, so you look at the plane perpendicular to the tilt plane. That is the area of interest, and that gives you much interesting features. So very clearly you see that at this particular angle you have a maximization of the TSAM. So this was also very nice. The calculations are very, very intense because you have to now go to a different reference frame, and the entire geometry of the problem changes. It is very non-trivial, but that Shobik has done very nicely. And so this was also something, I've not shown this, but we also looked at the Belinfante spin here. And what we actually saw is that the electromagnetic democracy is broken here. So you do not find the electric part and the magnetic part to be same. The RCP and LCP actually are different for SX and PY. So this was a very interesting thing. It was, these kind of, we didn't do an experiment here. Shobik is now trying to do an experimental. So what you also generate here is orbital angular momentum. Because of that tilt, there is a phi gradient straight, and therefore there's a del phi. So orbital angular momentum we should be able to see. Transverse spin seeing by tilting is very tough, exceedingly tough. But one can actually try because one can probably put those liquid crystal particles and see. But orbital momentum you should see some kind of rotation. So you come in with circularly polarized Gaussian beam, you tilt the interface, you will generate OM. Okay, so those experiments are ongoing. This was the paper, and finally, yeah. So summarization. I don't know what it's possible, but if it's necessary, rather. But essentially, I've tried to give you a flavor of what it takes to spin particles. I mean, spinning particles by getting the transfer of spin angular momentum conventionally is very simple. But due to spin orbit interaction effects, you have extremely exotic kinds of rotation, which is both spin and orbital. And you see beautiful coupling, dependence of the orbital motion on the input helicity. And most importantly for me, not knowing literature is very useful to be creative. Thanks. Yeah.
Open for questions. I was thinking while you were giving the lecture, this tilting of the stratified media is a very nice idea. But I was also thinking that is it not possible to engineer, let's say, a gradient?
Absolutely.